Hello. And this one. Okay. Wait. Sorry. Let me see which one is the correct connection. This one. Okay. Yeah. Sorry for the delay. And any question this time? This time we start talking about this global algorithm and also go over the IBNQ. So hopefully everyone is okay with doing IBNQ calculation. And anyway, this time we go over almost everything about global algorithm. I guess we go over the most important concept of global algorithm. So let's have a quick recap. So global algorithm is combined of start from all the way up here. Okay. So global algorithm is very simple. It starts with you create equal superposition, and then you need to keep doing those global iterations some amount of time. Okay. And and I guess we should go back a little bit. So the global algorithm is an oracle algorithm that help us to solve this search problem. So we assume have an oracle that's expressed like a small and big function, and so it has so the truth table of this small and big function is a big and big string. And so you want to find, is there any one in this big and big string? Or in terms of the small and big function, you are saying you have this f of x from n bit to 1 bit, and you want to find a mark item inside the input to this f of x. So you want to find a small and big string x such that f of x equal to 1. Okay. If such f of x exists. If f of x is just constant 0, then you need to answer there is no such mark item. Okay, and this is the oracle problem. So this small f of x is given us as a quantum oracle or sub f, and now you want to. So now we focusing on minimizing the query complexity. So we want to use as little query as possible to answer this search problem, finding a mark item. And with a quantum algorithm, where you will need to put multiple oracle inside your algorithm. And where we put the oracle inside this global algorithm is in this big G. Okay, so back to talking about what's global algorithm is you start with 0 and you apply a whole bunch of headema to create equal superposition, which you call psi, and then you just keep applying those G get I guess G is unitary. You apply those G block of G unitaries whole bunch of time that we'll talk about later. So about order square root and time, and then you do measurement, and you will find the mark item. And this G is written as 4 step. So first is you apply your oracle. So each G you will need use one oracle's construct. And then there are those 3 steps. So there are this headema, and have this weird phase shift on x and headema. And those 3 steps together, we say is actually it's a reflection around this side. Okay. So G is 2 reflection. One reflection is the oracle, which is actually the face version of the oracle. And another reflection is the other step that doesn't involve the oracle. They don't depend on the function the hidden function f, but they are still reflection. They are reflection around this state side, and it has this from 2 side minus side. Okay. And these two reflections, then we have this geometric way to analyze how this algorithm will actually affect the state. So we will look at time step by time step to see what is the quantum state at each of those locations after each application of the global iteration. Okay? And it has a very geometric interpretation, and then from the geometric interpretation, we'll know when should we stop applying G and just do a measurement. And the geometric interpretation is that we have two reflections. So let's scroll all the way down here. Okay. So we have psi here, and then we consider the two-dimensional plane that's spanned by your psi, totally the uniform superposition of every computational basis with dimension bigger, and then this beta, that's the uniform superposition of all mark items. Okay. And yeah. And so the two-dimensional space, you can easily find out that the vector that orthogonal to this beta is alpha. That's a uniform superposition of everything that's not mapped. So every computational basis state, that's not the mark item, and this is all computational basis state, that's the mark item. And then what are the two reflections? Then we see that if you apply your oracle OF, then it's a reflection around alpha, because you write a vector in, I should have it somewhere. Yeah, here. So the first reflection OF will be a reflection around alpha because it negates the beta component. And then, then as we said, the other thing you do is a reflection around this uniform superposition side. Okay, so each global iteration is a reflection around alpha, then reflection around psi. And with some simple geometry, you prove that so each global iteration, the net effect is you rotate your state by angle theta in this two-dimensional space. And then our state starts in this phi, and then after you do those two things, you start with this phi in this two-dimensional space, psi in this two-dimensional space, and because both of the reflection doesn't map anything outside of this two-dimensional space, so the state will just keep rotating inside this two-dimensional space. Okay, and okay, back to what we were saying. So the net effect of those two reflections is rotation by angle theta, where theta is defined by is twice over this theta over 2. So theta over 2 is defined by the angle between psi and alpha, and you can calculate that. Okay, so this is something we'll use today, and we can calculate that the theta can be calculated from n and m, where n is the total number of items and m is the total number of mark items. And so sin theta over 2 is the inner product between beta and psi, and it's square root n and n. Okay, and so we know that the state will keep rotating on this unit circle, and its angle to alpha is k plus 1 over 2 theta, where k is how many global iteration you do. Okay, and now we can finally determine when do we want to stop our global algorithm. We want to stop our global algorithm when our state is closest to our beta here. Okay, because beta are all the mark items. So if your state is close to beta and you do computational basis measurement, you will get a computational basis that's very likely to be very likely to be a mark item. Okay, because it's something inside beta. Okay, so yeah, so you want to rotate it to about theta over 2 and do computational basis measurement, and that means the number of rotation you need to do, which we call R, is about pi over 2 divided by theta. Okay. So we have R plus 1 over 2. Theta is about pi over 2. So we want to rotate it up to about 1 over 2. pi over 2. So r is about pi over 2 divided by theta. And then we have theta has this relationship, so this is about pi over 4 square root n over n. And it makes sense because the more item you are searching from, the longer it will take. And if there are more marked items, then it's easier to find a marked item. Okay, and I think that's about this time. And any questions so far? If not, then let's keep going. Okay, so let's go to more detail about this. Okay, so first, what's the error probability? Okay, so for now we assume we know m. So we know m, and then we want to rotate to something that closest to beta here. Okay, and so if we rotate to something closest to beta here, then there will be some but each time you are rotating theta angle, right? So you cannot. So if theta is not like a very good number, then then you can overshoot a little bit or undershoot a little bit. And but the amount you overshoot or undershoot should be less than theta. Otherwise, you can find something closer. Okay, and yeah. Okay, so anyway, so the success probability is actually sine square this total theta. Okay, so sine square k plus 1 over 2 theta, because that's the probability you get something inside beta, and cosine square this total theta is the probability you get something in these among items. Okay, and that's okay. So probability of failure is cosine square theta, so we say it's cosine square total theta, so the component on this alpha. And okay, and then we just do a little calculation. So it's cosine square this thing, and then we want to see how far away is this thing from pi over 2. Okay, so k plus 1 over 2 theta, we say it's very close to pi over 2. So it's pi over 2. Sorry. Okay, so we do some manipulation here. So cosine square this thing is sine square. So cosine square x is sine square pi over 2 minus x. And we know that pi over 2 minus thing is the delta, so it's the difference to pi over 2. And yeah, so this area is cosine square k plus 1 over 2 theta, and that's about sine square delta. And as we know, sine square delta is less than theta over 2, so that's less than sine square theta over 2, which is equal to n over n. Okay. So you see the error probability is pretty small. As your n get bigger, then this will get smaller. Okay, and okay, so we have a very good error probability. Okay, and okay, now go to the tricky part. So the annoying part about global algorithm is that all the analysis above require we know m. Okay, we need to know what's m, so we know how do we stop around this delta angle here, delta error there. And if you don't know m, then you just keep running global iteration, you might overshoot, because we know our algorithm will rotate around this plane, and only draw up to this pi over 2, but you can imagine if you keep going, then you will just run around this circle, etc. Okay, and yeah, if you run around this circle and you will have highest success probability here, then success will get lower, etc. You go up and down, and the success probability is like this. It's sine square the total angle, and sine square function look like this. It's between 0 and 1. And so this is a plot between our success probability and the number of iteration we do in our global algorithm. And we see that if our number of iteration is about this power 4 square n over n, then we have around 1 success probability. We have a success probability 1 minus this small number. But if we keep going, the success probability actually gets smaller and bigger, and smaller and bigger. Okay, so that's annoying. And but let's talk about good part. So if you actually know m, so you can even get rid of this thing. Okay, you can, yeah. So if you know m totally, then you can actually adjust your algorithm a little bit. So you try to make this angle theta a bit smaller, so that you will rotate. When you rotate r times, then this delta will be 0. You will exactly hit beta here. Okay, so that's pretty cool. If you know m, you can have success probably 100%. And I don't know. Yeah, this can be homework, but we might be a little short in. We'll see. Yeah. And okay, but back to don't know m. Okay, so if you don't know m, then there are multiple ways you can do. So if you don't know m, that's actually not a too big problem. Will depend on what you do. If you only want constant success probability, then it's okay. We'll see later as the graph. So that if you don't know m, then you actually cannot get 100% success probability. But if you only want constant success probability, you can get pretty good. And there are many ways. Okay? So the textbook way is that you do quantum counting to estimate m first, which we'll see. But it's kind of expensive to do, as we'll see. Okay. And okay, so let's talk about another way to do this if you don't know m. Okay. And if you don't know m, then you can actually kind of just do binary search on m. Okay. The idea is that you start with you start with assuming m is very big and kind of getting smaller and smaller in an exponential series. Okay. So you start with assuming n equal to n, and then n equal to n over 2, and n equal to n over 2 squared, etc. I guess I should write. Oh, it's probably okay. Okay, and why does this binary search sequence work is because so your m will fall. So first of all, this so there are a lot of those things, but it's actually okay, okay. Because so this sequence will be so if you think about this sequence, then its length is about I forgot to connect. Okay. The number of turns here is about log n, but actually you don't even get extra log n factor. So first of all, so if you do all those things, then then okay, and so there are about log n turns. Okay, but actually you only need extra 1 over 1 minus square root factor. In the number of go rate iteration to do. Okay. Because what you are doing here is you try go rate iteration equal to 1, because here n over n equal to 1, and then go rate iteration about square root 2, and about square root 2 squared, etc., until all the way to then this will end with about 1, right? And 1, when n about 1, then you have square root n over square root n over n. Okay, and so you see this is a geometric series from 1 to square root n over n, and with the factor being each time you need to do about square root more queries, square root times more query, right? Is a geometric series with the factor being square root. Okay, and but we know that so if you have a geometric series that's so basically the geometric. So if we think about this series in our direction, it's about square root n over m, then square root n over m divided by 1 over square root 2. So if you think about this, and plus square root n over n divided by 1 over square root 2 squared, then it's a geometric series with a factor that's 1 over square root 2 and getting smaller and smaller. And then we know that even if we add up infinite terms, then this sum up to a finite number. So this thing will be about square root n over m times 1 over 1 minus r, right? And 1 over r is 1 over square root 2. So that's, so I write this wrong here. So it's, yeah. So this thing, it should be, yeah, 1 minus 1 over square, 1 over 1 minus 1 over square root 2. Okay. So actually, you are only getting this extra factor, and this is a constant. So this is how many extra query you need to make, how many total query you need to make. It's still square root n over m, just with this extra constant factor. I guess if you want to count constant factor, they should be also powerful. But so these are order, okay? And these are constant factor, so this doesn't change a big O. Okay, and yeah, so we see that if we try all those n, then the number of query doesn't change too much. And then we also need to say this is okay enough. And this is okay enough, you can do analysis. So how okay this is will depend on how big the threshold is between. But basically the idea is that your true n will be between one of those two, right? So there will be some n to the k and n over 2 to the k plus 1, and your m will be between here, and then you know m will be like m will be kind of close to those two numbers, right? Because there can be a most, so the relative error to m is about is at most, so you know like this is at most twice m, and this is okay. Sorry, this one. So this one will be at most twice m, and this one will be at least n over 2, right? And because there are like only there are only twice the difference between them. Okay? So you know this thing is I guess we don't need to write down. Okay. Yeah, so both of those are constant factors away from m, and so when you do global search, then then you can analyze that if your m got like a constant factor difference, then how much your overshoot can be. Okay, and okay, I guess angle is okay. Yeah, so yeah, so I guess angle you can overshoot about about square root 10. Okay, so sin theta, yeah. So you can go back to theta, and so if m you so if you overshoot m with a factor of 2 here, then your sin theta will overshoot with factor over square root 2, and so you still get a constant probability. And obviously, if you change a 2 here to a small number, okay, so if you want to do better, then instead of 2 here, then you can do like n over say 1.01. Then we'll have a pretty good estimate of m here, and but then you plot with a bigger constant factor, so you will have 1 over 1 minus 1, 1 over square root 1.01, etc. Okay. But anyway, so this is a binary search idea you can do, and I think if you do about square root here, and you will be already pretty good. And we have a test with, yeah, I had some undergrad 20 cents try this, and yeah, we had a pretty good result to do this binary search. Okay, so that's about the easier way to estimate n if you don't know it. And but there is Harder way to do this is you do quantum counting to estimate. Okay. And so this is what the book, this is how the book motivate quantum counting. But quantum counting is actually something more powerful to estimate, and it kind of estimate in a poor job anyway. But it's pretty useful. So let's talk about quantum counting. Okay. And so what does quantum counting do? So quantum counting, as we know, is very related to Go research, and you want to SAM to epsilon error, to some error. Okay. And well, I guess before we go to quantum counting, anyone has any question about why doesn't know M is a problem and why we can do binary search? If not, okay, I guess I should. Okay. Yeah. Then let's talk about quantum counting. Okay. So quantum counting is a very general thing to, very general algorithm to SAM. So once again, the setup is like over search. So you have input string small f of x, and you want to find the mark item. You want to find the, okay. So now it's different. So the input is the same. You have f of x with NB input, and so yeah, that's right. So input is still f of x, and it's from NB string to 0, 1, and you want to, and it has some mark item. So marked is f of x such that f of x equal to 1, and unmarked are the others, and we don't need to say. Okay, and now the quadrant is want to find m equal to number of marked. Okay, and but now there are tricky part. So tricky part is, a bit tricky is you want to estimate this to epsilon, like how you define the error. Okay. So obviously you can ask like you want to get this exactly, but that will need a lot. Okay. So there is an extra parameter you can tune here, which is the error to this n. And here we'll parameterize this by multiplicative error. That means, so we say we want to estimate out to epsilon multiplicative error, and that means the difference. Okay, so the difference between your estimation and the true m is about epsilon times the true m. Okay, and then we'll see that we'll kind of see that there is a quantum counting algorithm that do this with 1 over epsilon square root n over n query. Okay. So it depends on, so obviously the epsilon is smaller, then you need more query, and then other part is similar to Gover, so it's square root n over n part. Okay. And then we can see a bit of an example of what epsilon we want to pick. So maybe you want to pick epsilon such that delta m equal to 1. Okay. So you want consecutive additive error, so this is like delta m equal to 1. Oh, sorry. So ex delta m equal to 1. So you want to know basically your m exactly. Then so delta m equal to 1, then epsilon will equal to 1 over m, right? So that means epsilon is 1 over m, then this 1 over epsilon is m here. So we will need square root and m queries. Okay, and yeah. Okay, so then you see this is a little different from Gover search before. So because Gover search, so if there are m mark item and you only want to find one of them, then it's square root n over m query. And I guess I should write big O. Okay. And yeah, but you see that if you want to find all of them, I guess you didn't find all of them, but basically the same. Okay. So kind of you want to find a number of market items, then you need to go do the square root and also you basically this is finding all of them. You can find all of them with about this number of query too. Okay. Okay. So there is a subtle difference when you have multiple market items. But back to estimation. So we want to SAM to some epsilon multiplication error. And how do we do this? We actually combine the two different chapters we talked about. So we combine our Grover algorithm and phase estimation. Remember, this is how we do Shor's algorithm. Okay. So we do phase estimation to the Grover iteration G. Okay. And yeah. Okay. But we have this funny tricky point. Now we are estimating n, but we still don't know n. Okay. So this is something we need to check about. Okay. Because all the global thing we kind of assume we know n, but now how do we do this without knowing n? Well, I guess it will. Yeah. Since to do this thing, you don't we need to know n, but later we'll see that it still gives us some problem. Okay. But anyway, so what happened when we do phase estimation on global iteration? And so once again, remember what's global iteration. Global iteration is a rotation by a single theta. Okay. And so in our favorite alpha beta basis, the two-dimensional space, you can the rotation matrix is a rotation matrix, and it is this thing. So cosine theta minus sin theta, sin theta, cosine theta. You can easily verify this is a rotation. Okay. And then you can diagonalize this matrix and find out the eigenvalue of a rotation operator is e to the I theta, e to the I 2 pi over theta. Okay. Okay. So this is those two are the eigenvalues of Grover iteration in the 2D subspace that will fix us in. Okay. And to make things a little easier, first we assume that we make our n a little bit bigger. So we just append a whole bunch of 0 to our f of a's input. And so then we make a theta less than probably 2 will make some calculation easier. Okay. I guess let's go through high level for now. Okay. Very high level. Wait, we have. I'm not sure we have time to go to detail. Okay, so let's go to high level first. So let's ignore this. And anyway, let's talk about the phase estimation. Okay, so phase estimation you can find that so G has a phase e to I theta e to the 2 pi minus theta. Then so then you can kind of see how we get m here. So phase estimation, then we will learn theta, or 2 pi minus theta. But if you see 2 pi minus theta, then you can just subtract 2 pi from this, then you will get theta. Okay. So you will basically estimate phase estimation. You will learn theta, and we know sin squared theta over 2 is n over n, and so from theta and this equation, then you can estimate your m. Okay. Because n we know, okay. N is public, so you know theta, then you go to this equation, then you know m. Okay. And so this is the basic idea. You phase estimation on G, then you will know theta, and then you classically calculate what the corresponding m is. Okay. And then what is all those calculations about? All those calculations are about how to deal with epsilon. Okay. So this is all about calculating what kind of error you have in your phase estimation. So what will happen is when we do phase estimation, and the phase estimation is not perfect, so you have some error on your theta, so you have some delta theta here, and then we do a whole bunch of calculations to see how that delta theta affect the delta m you have. And remember, delta n should be about this thing. So delta n is your epsilon times m. Okay. It's additive error to your m. Okay. And so we'll transform the errors back and forth. Okay. So that's a high level idea. And and the result should be the result is like this. I guess the result is already we showed before, so we should get something about So we'll say get something by from delta m to be epsilon times m, then you will need 1 epsilon squared and over n queries. Okay. And okay, we have about 10 minutes. Let's see how many detail we can get. Okay. And so here, I guess we cannot go into total detail, but total detail is a bit boring. So let's go into a bit higher level calculate, still higher level. So like on the left hand side, okay. Still a bit higher level calculation of how to estimate this delta m. Okay. And okay, so before I estimate delta m, we need to do something that's a bit not too important. So we need to introduce another notation as delta, okay? Because this thing also depends on the success probability of your algorithm. So actually, this counting estimation sometimes it will fail. It will fail. You will, so only 1 man's delta probability will get correct estimation of n to the correct multiplicative error. So there is another error probability to the algorithm, and we call it delta here, and the book uses epsilon, so it might be a bit confusing to you. But anyway, so as soon as we have this delta, and then we use then we say the some two parameter that will be determined later. So we say our phase estimation if we use t-bit, and then if we so more like if we want phase estimation to have n-bit of precision, then we will need to use t-bit, where t is n plus this extra delta dependence term. This is something that we claim in the phase estimate when we discuss phase estimation. Okay, and so this is some m, and what does this m will do? M will say that if we have this m, then we will say the error on delta is less than 2 to the minus m, because the error on theta will have it will be less or equal to 2 to the minus m, because you have m bits precision on theta. Okay, and then we can so skipping all the detail. But this thing is very important, so let's highlight it. Okay. This is a starting point. Delta theta is about 2 to the minus m. And okay, so let's do this the sketchy or calculation sketch here. So we know so how does theta relate to mn? Okay, so we have sine squared theta over 2. I guess let's write this back. Okay, so let's do a rough estimation. So we have sine squared. That's right here. So sine squared theta over 2 equal to n over n. Okay, and then now we start the approximation, and we assume theta is small. Okay, we assume theta is small, then sine squared theta over 2 is about theta over 2. Okay, and and we also get HR 2, but that doesn't matter too much. The HR over 2, HR 2 on n is because we take n become 2n here. So that's also have a 2 here. And so we get HR 2 here because we just make n to 2n. And anyway, so sine theta over 2, sine squared theta over 2 equal to n over n. So that means theta over 2 squared is about n over 2n. I guess also 2n here. And then we do something that physicists want to do a lot. That is, we try to take the derivative on both sides. Okay, this is something funny. So here, this is the function on theta, right? And here it is a function on m. Okay, and so what we are doing is we kind of take a derivative on both sides. So we take a derivative of theta on this side, and so we have like f of theta equal to g of m, and this will mean f prime of theta d theta will equal to g prime m dm. Yeah, although this is funny, but I guess like let's try to write a more okay like weird justification. So this is some trick we are doing. So we have f of theta equal to g of m, and so what we are doing is like we have df d theta will equal to dg dm dm. This is what we are doing. And we say d theta and the dm is like this delta theta and delta m. Okay, and yeah, so we calculate the df d theta here. So then it's a chain rule of differentiation. So we take out these 2 and theta over 2, and then 2 and because it's square, so you have 2 times this thing inside, and then you have differentiation of this against theta. So it's just 1 over 2, and then the theta here, and then the differentiation here is linear in m, so that's just 2 over n. Okay, so we do this funny trick here, and so then we can get the relation between d theta and dm, and so we see that, but we want to express dm in terms of d theta. So dm is about to move things around or to cancel out. So dm is d theta and times theta, and then is n here. So n times theta d theta. Then then we want to and then we want to express this theta in terms of n again. Okay, and so from here theta is about square root 2n over n, and yeah. So we put everything together, then you see that dm is about the square root 2n d theta. Okay. And yeah. Okay. And okay, so that's put things back. So dn is about square root 2n d theta, and we know d theta is about 2 to the minus m. Just the thing we said before, because theta has MB precision. Okay. And so the number of query is about 2 to the t, because that's how many query we need to do for phase estimation. Okay. Right. Remember the phase estimation, and we say you want TP precision, you actually need 2 to the t bit. Sorry, 2 to the t cos to your unitary here, and in Shor's algorithm we can get away from this, because you have modular exponential. But here this u is actually contains u here is a Gover iteration, and yeah, so it's a Gover iteration, and we don't have Gover iteration contain oracle, so we can actually do modular exponential on oracle. Okay. So there you need to actually do exponential number of calls to this u, and in particular you need 2 to the t calls to this u. Okay. Okay. So total Gover iteration you need to run is 2 to the t, and that's just query complexity, and so the query complexity is also about 2 to the t, and so t is about m, right? T is almost m with some delta factor. So let's ignore the delta factor now. Then we see the number of query is about 2 to the m. Okay, and yeah, so that's combine everything together. So our delta m is, so we can now make it 2 to the n as just 1 over number of query. 2 to the minus n is 1 over 2 to n, so it's about 1 over number of query. And so delta m is about square root 2n number of query, and the number of query is about 1 over delta n square root 2n. Okay. And okay. And I guess so. This is about the thing we show here. Okay. And And then finally, finally, then we can connect this to how to the epsilon, right? So I guess okay, so we connect to here. So we pick epsilon about, so on our delta n about epsilon n, and then so I guess that's right here. So our delta n is about epsilon n. Then number of query will be about 1 over epsilon, and let's get rid of these two because it's kind of extra. It's not needed. Okay, about 1 over n, 1 over epsilon, and then this 1 over n will cancel with this square root n, and so yeah. So number of query is about 1 over epsilon square n over n as we can. Okay, and but okay, so let's fix this here. It's kind of important. Okay, but then there is this red text part. Okay, so if you actually want to get this, there is a problem as we say about it, because if you want to pick t to have our constant epsilon, then we need to know small m, and if we need to know small m, we need to know big M, and they kind of now we see you are kind of circular, right? So you want a fixed epsilon probability for any m, then these oscillations don't actually give you, because you need to fix because you need to fix t pick the correct t at the beginning. But we can still do something, so this is what the book do. Okay. So if we don't know m, then we can just pick t that's good for us. Okay. So they pick t to be about square root n queries. Okay. And then you can plug the number here. So, or more like pick t's. So if you don't know m, but you can still fix on q, like, so say if you fix q to be 1 over square root n, right? So fix q to be 1 over square root n, then you can determine where t and n. Then square root n will cancel this square root n here. Okay. Then your delta n will be about order square root n. Okay. So yeah, so this is not a fixed epsilon, but you get something that's still pretty good approximation. So we know that if you pick square root n query, you can get about square root n precision. Okay. And so we're out of time, so maybe let's continue on Thursday to see more detailed calculation, and also can do some clean about the algorithm that's a bit better in some sense. Okay, and no question. Let's stop for now, and see you on Thursday. And also something I will probably announce on Thursday again. That is, remember next week I will not be here, and but I think we are very good on schedule. So I think next week I will just let you watch some of last year's video, and it's probably on the last year's video on the not so like a more branching out part of the course. So maybe on RSA and maybe RSA and something. Yeah. So but for the main algorithm part, so like a global algorithm and Short's algorithm, we will still do like this year's new videos. Yeah. Okay. So that's it. So see you on Thursday.